Okay, so our next and last speaker of this session is Yong Cai, who is going to talk about modified gravities in non-singular cosmology. Please.
Okay, thank David. I would like to thank the organizers for organizing this wonderful online workshop. My talk is about the modified gravity in non-singular cosmology. I just realized there are many speakers talk about a lot of details about modified gravity, so maybe I should spend more time in other sections. There are 4 sections in my talk. The first section is about motivation for studying non-singular cosmology. The second section is modified gravity in non-singular cosmology. And in the third section, I would introduce EFT method. And the last section is a short summary. We already have inflation. Inflation is so successful. Inflation is a possible solution to the horizon problem, the flatness problem, and a lot of other problems of the hot Big Bang cosmology. More interesting and more attractive is inflation predicts nearly scale invariant scalar probation. The result is consistent with the CMB observations very well, as we can see from the theoretical prediction and the data of Planck 2018. Inflation also sets the initial conditions of the hot Big Bang expansion. Inflation is so successful, but inflation may not be the only solution to the horizon, the flatness problems. As we know that there are some alternatives to inflation. For example, the equipyrosis or the genesis. Inflation is geodesically incomplete in the past. However, the prediction of the scale invariant power spectrum of scalar probation depends on the initial state of perturbation modes. There is a well-known Trans-Planckian problem. In unitary gauge, the quadratic action of scalar probation zeta can be written in this form, usually. With a quadratic action, we can obtain the equation of motion by some redefinition. In the slow-roll inflation, this equation can be solved in the standard way. The solution looks like this form. Here, nu is about 3/2 for the slow-roll inflation, and the CS, the sound speed of scalar perturbation, is just unity. In order to find the undetermined coefficients alpha and beta, we need to set initial condition. By requiring the perturbation modes coincide with the Minkowski solution in the infinite past, or by requiring that the perturbation modes deep inside the horizon looks like the Minkowski solution, we find that alpha should be unity and beta should be 0. Of course, there could be some phase factor, but it's not very important. And this solution gives nothing but the Bunch-Davies vacuum. Setting the initial state of perturbation modes as the BD state is essential for inflation to predict the scalar invariant power spectrum of scalar perturbations. And this method seems natural since for perturbation modes deep inside the horizon, in the equation of motion, this term can be subdominant. However, the wavelength of the perturbation modes is proportional to the scale factor. And for the inflationary background, the wavelengths inevitably become smaller than 1/λ before some time. Here, lambda is a cutoff scale of the effective field theory of inflation. When lambda gets smaller than such a length scale, the higher order derivative operators surprised by lambda may no longer be negligible. For example, operators such as this one, these higher order derivative operators will appear. And the dispersion relation will be modified. So requiring the probation modes to coincide with Minkowski solution is no longer sufficiently reasonable. And this is a Trans-Planckian problem. Recently, a conjecture named the Trans-Planckian censorship conjecture is proposed by Roya and Wafa. According to this Trans-Planckian censorship conjecture, probation modes deep inside the horizon, I mean probation modes that are sub-Planckian initially, can never cross horizon and become classical. This conjecture suggests that inflation can only last for a limited folding number. And the upper bound depends on the Hubble parameter or the energy scale of inflation. The constraint of the Trans-Planckian censorship conjecture can also be understood from the power spectrum. If we neglect the higher order operators, we find that UK, namely the probation mode function, is 1 over square root of 2k. For the sub-horizon probation modes. And we know that zeta is proportional to UK over A, so it's proportional to 1 over A. Zeta is decreasing with the expansion of the universe. At the beginning of the inflation, the spectrum of the sub-horizon probation modes can be written in this form. So if P zeta of TF is evaluated at the end of inflation, then the form is standard. So we find that the validity of the probation theory requires that P zeta should be smaller than unity. Otherwise, the overdensity of scalar probations will produce a lot of black holes, and the space-time will be distorted on the sub-horizon scale. And this inequality reproduces the Trans-Planckian censorship conjecture, since if the slower parameter epsilon f is evaluated at the end of inflation, it is also of order unity. A similar analysis can be carried out for the tensor probation, which gives exactly the same constraint as that of the TCC. So TCC might suggest that the existence of a pre-inflationary or alternative evolution. According to the Ricciardo equation for the null-J Odysseus, where we have neglected the shear term and the rotation term, if the null convergence condition is satisfied, then we find that d theta over d eta must be negative. Here, eta is a affine parameter of the null-J Odysseus. So in this situation, inflation or the universe that satisfies these conditions cannot be possibly complete. That means that the wavelengths of the probation modes will be blue shifted in the infinite past, and the physical wavelengths of the probation modes be smaller than 1 over lambda. In this situation, the neglected higher order derivative terms cannot be neglected. Therefore, only if the pre-inflationary era is past complete, it is possible to set the initial state of probations in the infinite past as a Minkowski vacuum. The past completion requires that the NCC or equivalently the NEC when Einstein gravity is satisfied requires that NCC must be violated at least for some period. That means that the Hubble parameter must be the time derivative of Hubble parameter must be positive at least for some period. There are two popular scenarios. One is a bouncing scenario, where the universe is slowly contracting initially, and then after a non-singular bounce, the universe becomes expanding. Another scenario is the Genesis scenario. The universe originates from the Minkowski spacetime in the infinite past and expands slowly. In these two scenarios, the surprised high-order derivative operators are negligible. These two scenarios are also consistent with the Trans-Planckian censorship conjecture, since sub-Planckian perturbation modes can never have the opportunity to cross their horizon. Since the spacetime is Minkowski in the infinite past, all perturbation modes can automatically prepare the initial state required for the inflationary perturbations at the CMB window, hence can be consistent with observations. Then we go to modified gravity in non-singular cosmology. There are many kinds of modified series of gravity. However, in this talk, we will focus on the scalar tensor series. The study of inflationary cosmology suggests that we should pay attention not only to the evolution of the background evolution, but also to the evolution of perturbations in the study of non-singular cosmology. In unitary gauge, the quadratic action of scalar perturbation can be written in this form. QS, a positive QS and a positive CS squared is required so that there are no ghost or gradient instabilities. Here, CS is the sound speed of the scalar perturbation, and QS is related to the effective Planck mass. For very simple scalar tensor series, such as a series where there's a function P of phi and x, we can calculate that QS and CS squared for the canonical single field scalar tensor series, where P, the second derivative of P with respect to x is 0, QS must be negative during the NEC violating phase. So with a non-zero PXX, however, the sound speed squared is still negative during the period of NEC violation, since here CS squared is proportional to epsilon. Epsilon takes the same form as that in inflation, namely the slower parameter, but here it is not a slower parameter. For the cubic Galilean theory, the form of QS and CS squared are more complicated. Again, we can guarantee that QS is positive so that there is no ghost instability. But it is still very hard to remove the gradient instability from the evolution of the scalar perturbations. Here, gamma equals h minus this term. So the NEC violating phase is no longer overlap with the period where instability appears. It is found that the gradient instability can be removed from the ANC violating phase, but it is later proved that such instabilities still exist in the entire history of the universe. There is the no-go theorem. The no-go theorem is first proved for the cubic Galilean. It states that healthy non-singular cosmological models based on the cubic Galilean does not exist. Then such proof is generalized for the full Horndeski theory. That's to say, based on the Horndeski theory, we cannot construct healthy non-singular cosmology. It is pointed out that there could be a loophole. And this loophole is related to the strong gravity problem. I think Julia will give more details about this topic. So the exploration for healthy non-singular cosmology suggests us to find the solution in beyond Horndeski theory, or even more general, degenerate high-order scalar tensor series. The EFT method, the effective field theory method, is a powerful tool for investigating the problems of perturbations in cosmology. The EFT of cosmological perturbation is widely used in cosmology. It is first proposed by these people in the study of inflation, and then it is used for the dark energy. In unital gauge, the EFT action is written in this form. The background evolution is only determined by the first line. And there are only quadratic terms in this action. The higher order terms are not written here. Many modified gravity series, especially the scalar tensor series, can be mapped to this form at quadratic order. For example, for the cubic Galilean theory, we can find these coefficient functions, and also for beyond Horndeski and beyond Horndeski series, modified gravity series such as the FR theory or the Gauss-Bonnet theory can also be mapped to this EFT form. We can calculate the quadratic action for the perturbations. Based on this EFT action, the quadratic action of the tensor perturbation takes this form. The tensor perturbation is quite simple, where Q of t be larger than 0 and the some speed squared of tensor perturbation be larger than 0 are required, so that there are no ghost and gradient instabilities. For the scalar perturbation, the quadratic action are a little more complicated. Here, C1, C2, and C3 and C4 are some functions of the coefficient function in the EFT action. C1, C3, and C2 are complicated, while C2 looks quite simple. Then QS and CS squared can be expressed in this form. In order to avoid the ghost and the gradient instability, it is required that QS is positive and the CS squared is positive. So we have these two inequalities. These two inequalities are very important for the proof and avoidance of the no-go theorem. From these two inequalities with integration, we find that C3 at some later time Tf minus C3 at some initial time Ti equals this integration. This integration corresponds to the affine parameter of the graviton geodesics. For a partial complete spacetime, for geodesic complete spacetime, this integration should be divergent. So C3 must cross 0 at some time. For the Horndeski theory, where M4 squared equals M4 tilde squared, C3 is very simple. We note that there is a Qt squared. If Qt cannot be 0, then if gamma cross 0 at some time, we must have gamma. We must have a divergent gamma at some time. Actually, gamma should jump from minus infinity to positive infinity. If Qt is 0 at some time, then there could be the strong gravity problem. Well, in the beyond Horndeski theory, these two functions are no longer equal to each other anymore. In the original exploration for a stable non-singular cosmology, we consider this operator and consider such a very simple EFT action with these operators. We find that C3 takes this form. So in beyond Horndeski theory, if the second term in the bracket can cross -1, then C3 could cross 0 naturally without a divergent gamma. In this manner, the no-go can be avoided. With this EFT operator, we can totally remove the negative part of CS squared. The covariant form of this operator belongs to the beyond Horndeski theory. Okay, here is a short summary. Due to the past incompleteness of inflation, we think physics beyond inflation should be considered to set initial states for the inflationary probations. In non-singular cosmology, the space-time must be Minkowski in infinite past. Hence, it is natural to pick out the Minkowski vacuum state as the initial state probations. We find that a EFT method is a powerful tool for studying instability problem of probations in non-singular cosmology. This instability problem of probations in non-singular cosmology can be avoided in beyond Horndeski theory or more general theories, such as the general high-order scalar tensor series. Okay, that's all. Thank you very much.
Thank you for this very clear talk. So we have a few questions. Alex?
Oh, hi. So thanks a lot for your nice talk. I just would like to point out that, of course, people really do discuss this Trans-Planckian conjecture, but think of the following way. perturbations are really produced, so enhanced, right? Only at the moment of so-called horizon crossing. Before that, it's just vacuum, right? And also inside of the horizon, you can always introduce a reference frame which is not expanding, right? So because gravity, you may completely neglect on short scales, right? Just equivalence principle, you introduce Einstein elevator, and actually in Einstein elevator, you can introduce static frame, nothing expands there, and therefore you would not care about these modes at all. And so the only way how you start really thinking about any problems with quantum perturbations in inflation, it's when they really cross the horizon. Of course, if your horizon were Trans-Planckian, this would be a problem. But as far as there is like at least a small gap between your horizon and the Planck scale, it's all perfectly fine. So there is no problem with, formally, you don't need to extend the expanding frame back inside the horizon. It's not needed. It's just enough for you to have it around it. So that's just one comment. And second comment is,
thank you.
You would not care much, right, about incompleteness of even normal gravity in a sense, right? So it does not preclude you. Imagine you had singularity in the future. Why would you care if this future is infinitely far away? So in that sense, like for example, you cited Ijaz and Steinhardt. They actually had in the PRL paper, the universe existed 180 Planck times, as you may check, in total, and it runs from one singularity to another. So basically, from one infinite strong coupling scale to another infinite strong coupling scale, or if you want, from sound speed infinity to sound speed negative, well, imaginary. And the whole period of evolution is just 180 Planck times. But it's a kind of a funny situation there. But in reality, if you only have one singularity, then you're okay. So either you need to explain it, what is the birth of the universe, or you need to explain how to avoid it, some pathology in the future. But to avoid pathology in the future, it's very easy. You just decay it, you do some quantum process, let's say you do reheating, it disappears, and that's it. Then all the theorems, they don't cover that. Right? They cannot cover it because they only cover classical equations. It's a very powerful tool, it's very nice, but they only cover purely classical situation. So that's the thing. And in this, you cited our paper with G bounds, but in reality, we were showing this crossing and all this even before G bounds in this paper on kinetic gravity braiding. But it's okay. What would be more interesting for me, for example, is generically, people fight with ghosts, and the main thing is that the ghosts have infinitely, basically unbounded energy from below. But what one can check, then all these systems where you can violate null energy condition, and in particular all this, this braiding stuff, those, they all have actually Hamiltonian unbounded from below, but non-linear. So that's basically, it's unavoidable, because if you do allow for violation of null energy conditions, then your Temi nu is such that if your Hamiltonian density has anything to do with Temi nu, then that's it. Then it's basically some bounded from below. But that can be nonlinear instability, but we don't know how to estimate it. But honestly speaking, even for normal ghosts, there is no reliable estimation of the instability neither. That's kind of funny situation there. But yeah, thanks a lot. Sorry, David, for a long question.
No.
I think you have very helpful comments.
Okay, thanks.
Although I don't understand all of them.
No, don't worry. Write me a message then.
Okay, thank you.
Thank you, Joe.
So, Cheyu Chen for the next question.
Oh yes, thank you for the talk. So actually, I just realized that my question may have been responded by Alexander. But anyway, let me just try to clarify. So I understand that in order to have Bunch-Davies vacuum, we need to assume that in the infinite past, the spacetime is roughly Minkowskian. And I understand this can work for genesis model, but the bouncing model is quite, I don't know. So do we have to assume that it is Minkowskian in the previous universe?
Yeah, very good question. Actually, if the perturbation modes are produced during the pre-inflationary era, then the function a of t should I mean, in the infinite past, it should tend to some constant if the perturbation modes is able to exit the horizon during this period.
This
so
I don't understand.
In the infinite past, it is also the Minkowski spacetime.
So it cannot be others. I mean,
it could be other, but in that case, we may not be able to produce primordial perturbations during that time, or at that time the perturbation modes cannot exit the horizon.
Okay, because it seems to me that in order to have a similar Paul spectrum or the Morse evolution, what we need is just a contracting phase, which can like matter bounds or something. We don't really need to put some constraints on the very past. I mean, I don't know, maybe I'm wrong, but
yeah, there are many motivations for study non-singular bonds, for example, matter bonds or equiperosis. So in different scenario, the condition could be different, the situation could be different. Yeah.
Mm-hmm. Okay, thank you.
Okay, thank you.
Valérie, for the next question. Valérie?
Yeah. I have a couple of comments. One has to do with this Trans-Planckian problem. Let me continue with what Alex was saying, is that Trans-Planckian problem actually appears when you think that there was a sort of Lorentz violating very early stage. Then of course it matters what are the absolute frequencies and momenta. Otherwise you don't really care, because short distance, short moment, small moment and high momenta are related by boost, and if boosts are good symmetries, then you don't really care about Trans-Planckian. And furthermore, what there was quite a bit of discussion of this Trans-Planckian issue in the past, and what happens is that basically whatever you do, even if you violate Lorentz invariance at very short distances, still whatever you do, you don't get major effect on perturbations, scalar or tensor perturbations generated at inflation, unless your Hubble parameter is close to the Planck scale or Lorentz violating scale. Therefore, this Trans-Planckian problem is not that difficult for inflation, unless you resort to swampland and all this business. That's my first comment. The second comment is that you were talking about mentioning geodesic completeness for gravitons, and my comment is that once you consider massless particles like gravitons, then I don't think there is a good notion of geodesic completeness for these particles, simply because your geometry, which is felt by these particles, is depends on field redefinitions. You can make field redefinition or metric redefinition, go to make a, say, conformal transformation, and then the properties of massless particles, as far as geodesic completeness goes, these properties become different. So there's no well-defined, to my opinion, there's no well-defined notion of geodesic completeness for massless particles. So, so I think the argument based on geodesic completeness for gravitons is not quite strong.
Okay.
Yeah, and finally, my last comment is that, of course, in all these scenarios, bounce on genesis, you have to work hard to generate scalar perturbations with known spectrum, and also, and in particular, tensor perturbations is very, very difficult. So, I mean, that's another story. But there are mechanisms, but you have to invent separate mechanisms to generate scalar and tensor perturbations. Thank you.
Yeah, for your last comment, I think pre-inflationary theory, such as bounce inflation or genesis inflation scenarios, would be more simple for produce such perturbations.
No, the issue is spectrum. You want flat or nearly flat power spectrum, and that's difficult. There is no, I mean, in inflationary case, you have approximate scale invariance of your background, right? You may rescale the size and shift the time scale, and the sitter is invariant under such a transformation, and therefore there is a natural reason for the flatness of the power spectrum, scale invariance basically. However, here you don't have any good reason for scale invariance.
Yeah. Okay, thank you.
Okay, so thank you again for your talk.